Hi, this is part 1.3 of solid states. In this we would be studying about crystal systems and number of atoms in a unit cell. So in this, what we'll do is we'll look at all the possible structures that we can have in terms of crystals. I mean, how beautiful is that? You look at the total number of structures that we can have in terms of the crystal structures that are there. Perfect. Now, as I was saying, primitive unit cell. So for primitive unit cell, in which the atoms or the constituent particles that we have are only at the corners, we have 7 types. Remember this, get your brain cells activated. We have only 7 primitive unit cells. What are primitive again? The atoms or constituent particles will be only at the corners. So we can have only 7 variation of that structure that looks like cube. We can have only 7 variation in terms of angles or in terms of sides. Alright, so we have 7 variations of this. 7 variation of primitive unit cell, and in that primitive unit cell we have 7 different arrangement of the centered atoms. Alright, so the centered atoms can be either at the body center or at the face center or at the end center. So based on that, 7 centered. That is within this 7 variation of the primitive unit cell. So in total we have 14 arrangements. So these 14 arrangements are the only possible structures of crystal solids that we have. Alright, so we don't have anything different from this. So either the atoms will be within this or they won't be crystal. It's as simple as that. Okay, so now let's discuss what we call crystal system. So these 7 primitive unit cell types, different variations that we can have in 7 primitive unit cell, this is known as crystal system. Why crystal system? Because within this crystal system we have all the crystals solids that are there. That's why it is known as crystal system. There's a system under which all the crystals that are there in the whole entire world are classified. That's why crystal system. Alright, so there's a big box that I'm going to make. Just follow the steps that I'm going to do, because many times if you refer your books or if you see it anywhere, you feel it a bit hard to remember everything that I'm writing. So just see the steps that I'm following. What it would do is it will show your mind the steps that I'm following. Alright, so it becomes easier when you see the steps that lead to the whole structure. Instead of seeing the structure, at last you see it's a big task, but when you see each steps that are followed, the bricks that are laid, then the structure becomes an easy one that you marvel upon. Alright, so let's see this. So this is crystal system. So these are parameters. Then what we have is shape. Then we have variations. Alright. So crystal system. So before going on to crystal system, remember the conventions that we used while making the unit cell. The first unit cell that we made, A, B, C, alpha, beta, gamma. Just remember this. So the one which is kind of perpendicular is C, the base one is B, is A, and the one that is coming out is B. Alright, so this is the convention, and remember the angles between A and C, what is called, and between B and C and all that. So we'll use this, the same convention, and you will see how easy it becomes. Alright, so let's see. The first one that we have is cubic. So in cubic, what are the parameters that we have? We have A equals B equals C, alpha equals beta equals gamma equals 90 degree. So let's draw it. Let's draw the cubic one with these parameters in our mind. So what's the shape that we get? So firstly we draw C. C is the perpendicular one. Then we draw A. We have to make sure that A is equal to C. We'll name them A equals C. Then we'll draw B. B has to be equal to both C and A. Alright, done. All angles are 90 degree. Let's complete the structure then. Okay. So what we have is a beautiful cube. Alright. So I want to show you the structure as well. Where's the structure? Alright. So this is the structure that we have. Beautiful cube. What do we have? We have, this is C obviously. I'll show you this way. So this way, so this is C, this is B, and the one that is coming out is B. This one is A, C, and the one that is coming out is what we have, a B. Alright, so we have named it here B. Alright, let's move on. The second one that we have is Tetragonal. That's what we call it. So in this what we have, A is equal to B, but it is not equal to C. Alpha equals beta equals gamma is equal to 90 degree. Let's make it then. So let's make A first. So here's A. So A has to be, let's make C, which is not equal to either A or B. So C, I've made it a bit taller. Let me remove this. So C has been made a bit taller as compared to A. And then we have B, which is equal to A. To see the beauty behind it. Alright, let's complete this. Every angle is 90 degree. Let's complete this. That's the shape that we get. So that's a tetragonal. Remember the term. Remember the parameters. Let's move on to next one then. Alright. Next one we have is orthorhombic. What do we have? A is not equal to B, is not equal to C. Alpha is equal to beta, is equal to gamma, is equal to 90 degree. And let's try to draw this with the same parameters that we have. What do we have here? So we have A is not equal to C. And we'll draw B as well, which is unequal. Let's try to draw it here. And B is unequal to both A and C. Let's complete the structure. And that's the structure that we get. Perfect. Every angle is 90 degree. Alpha, beta, gamma. What is alpha? As you already know, between A and C we have beta. Between B and C we have alpha. Just remember these angles. These are simple angles. Alright, as we already discussed the method, the trick to remember the angles between the sign. So it doesn't matter because every angle is 90 degrees. So it doesn't matter where the angles are, but remember the angles between A and C, what are they called? Between B and C, what are they called? Okay, so the fourth one that we have is hexagonal. What do we have in hexagonal? Hexagonal, we have A equals B is not equal to C. We have alpha equals beta equals 90 degree. We have gamma equals 120 degree. Okay, so now let's try to draw a structure, a beautiful structure using this method. So what do we have? Parameters. So we have A equals B. So before that, what I want to discuss is, okay, so let me draw this first, so then I'll discuss that. Okay, so we have C, which is unequal. Let me draw C then. C is unequal. Then we have A equals B is not equal to C. That's what we have drawn. And that's what the structure looks like. And this angle is gamma is equal to 120 degree, and all the angles are 90 degree. So how do I know this angle is gamma? How do I know the top angle? The top angle is gamma. Okay, so now just see this. So the back line is A, alright. So this back line is also A. So what this makes is the front line is A, alright. So now if I talk B, so this, the line coming out is B. Now this is also B. Now this also becomes B. So A and B, the angle between A and B is known as gamma. Perfect. So do yourself the things that I'm doing, so it would be much clearer. Just remember the things that I'm telling you. So A and B, the angle is gamma is 120 degree. Perfect. Now let's move on. Okay, yeah. So hexagonal, as the name suggests, it has to be hexagon. Simple. Hexagonal, there are two hexagons separated by rectangular plates. Simple. It is also known as hexagonal prism. Let me draw that. So this is how it should have looked like. Alright. So these two hexagons, so this below one is also a hexagon. Okay. So these two hexagons separated by plates, rectangular plates. This is also known as hexagonal prism. So prism, what are prism? Prism are two surfaces, same surfaces, separated by rectangular plates. So like we have triangular prism. What do we have in triangular prism? We have triangles separated by rectangular plates. Alright. So now talking about this, so can I look at this? Can I make it smaller? Because unit cell is the smallest portion. That's how we defined it, right? So can I make this smaller than this hexagon? Yes, I can. How can I do it? So let me take a center point. So when I take a center point, now what I'll do is, you see, so I'll divide the hexagon into equal parts. How do I do that? You see, I joined the 3 points. So I formed 1, 2, 3. So 3 equal parts. So if I look at this, this is how it looks like. Alright? So this is clear now. You'll see in your books this structure. Why this structure? Remember this, because hexagon, I can break it into a simpler part, which is known as this, which is like this. Alright? So that's why hexagon is always shaped like this. Now fifth one, what do we have? Fifth one. Now fifth one, after hexagonal, we have orthorhombic, hexagonal, then we have trigonal. Okay, trigonal, or we also call it rhombohedral. Rhombohedral. I'll also tell you how to remember this, because you might think like it's a big task to remember it. I'll show you how you can like make analogies and how you can connect different things so that you remember this. Right, it's not a big task. Alright. Okay. So now if I talk about trigonal, in trigonal what do we have? We have A equals B equals C, alpha equals beta equals gamma, but none of them are equal to 90 degree. Alright. So trigonal or rhombohedral, I'll tell you why it is known as rhombohedral. First let me draw this. So let's try to draw this with these parameters. What do we have? So we have, so just look at this, the thing that I'm trying to do, because this is how you will be able to represent it perfectly. So this is how I draw it. Alright, so this is what is C, then I'll draw A, which is equal to C, then I'll take this line, this comes outside, and this is what I call B. All the lengths are equal. I fulfill my criteria, all the lengths are equal. Now see what I do here. Alright then. So see what I've done? So this face, if you look at it, it is a rhombus. That's why it is known as rhombohedral. 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 What is hedral? Hedral is face. Alright, that's the hedral. That is what hedral means. Hedral in English means face. So hedral is a Greek word. So hedral means face. So rhombohedral is rhombus faced. Tetrahedral is four faced. That's how things are named. Alright, octahedral is 8 faces. Alright, so rhombohedral is rhombus face. That's what we have. So we have A equals B equals C and alpha equals beta equals gamma. All angles are equal, but none of them are equal to 90 degrees. Alright then. Okay, so now we move on to monoclinic. Monoclinic. What do we have? A equals B is not equal to C. None of them are equal. Alpha equals gamma is equal to 90 degree. And beta is not equal to 90 degree. Alright. Let's draw the structure then. Hopefully we have space for the last one, the 7th one. Yes, we do have it. Okay, so now monoclinic. Let me draw monoclinic. So just see how I draw this. And you'll after I draw this, you'll see the reason why I do it like this. Okay. So this is C. I draw it slightly inclined. C. What do I have? None of them should be equal. So I draw it here. So this is A. And this one is B. So none of them are equal. And I complete this. Okay, I get a structure like this. So what criteria do I have? I fulfilled A is not equal to B is not equal to C. And now alpha is equal to gamma. Beta is not equal to 90 degrees. What is beta? Again, so beta is the angle between A and C. That's what beta is. So this is beta. Is this equal to 90 degree? No, it is not. It is inclined. So it is an acute angle. So beta is not equal to 90 degree, and the other angles I do have equal to 90 degree. Alright, so just work this out. We have fulfilled beta is not equal to 90 degree. Alpha and gamma, just look for it. You'll find alpha and gamma is not equal to are both equal to 90 degree. Alright, so this is the structure for this. And the 7th one that we have is triclinic. A is not equal to B is not equal to C. Alpha is not equal to beta is not equal to gamma. Alright. The structure, you can draw it any which ways. Let's draw it this way. Alright. So same, this is A, this is B, this top one is C, and this is B. Alright, so in this we don't have any structure that none of them are equal. Alright, so this is how it goes on. Now, let me just write the variations. After that, we'll go into how to remember all of these. So what are the variations? As I said, variations are the different. So we have primitive, that's the basic one, that's the default one. We will have it for every type crystal system that we have. In addition to that, we have centered, alright, end centered, face centered, and body centered. Alright then. So cubic we have primitive, we have end centered, we have body centered, then we have face centered. Alright, in tetragonal we have primitive, then we have end centered. In orthorhombic we have all of them. We have primitive, we have body, we have face, we have end. In hexagonal what we have is only primitive. In trigonal we have only primitive, And what do we have? We have monoclinic, we have primitive, body centered, and in this we have only primitive. Alright then. So what I want you to focus on is the different variations that we have. Let's count them. So there, 3, this is 2, this is 3. No, this is 4, sorry. Orthorhombic has all the 4. So 4 are possible, so orthorhombic has 4. This is 1, this is 1, this is 2, and this is 1. What's the total that we have here? 3, 5, 9, 10, 11, 12, 13, 14. So 14 is the total number of variations that we have. Remember this, 14. Now the question is, why 14? I'll discuss that. Before that, what I want you to do is just marvel this. Just look at this. And just remember, these are the different classification that we have, all the classification that we have of the crystals that we have all over the world, right? This is the classification. Just look at this, get a feel of this. And after this, I want you guys to meet the famous crystallographer, the physicist who discovered all of this. Alright, so now, okay, before moving on, let me just share few like simple, I won't say tricks, but few things that you can do in order to remember this, right? So how do you remember it? So this is the way how you do it. So you see, there is an order. You need to find a pattern inside this, so that it's all about pattern. That's what science is, studying patterns. So see this. So cubic, tetragonal, orthorhombic. Remember these as ones, right? So these are ones. So this is one group. What do we see in this? All the angles are 90 degree. Only variation is, first is cubic, everything is equal. What happens in tetragonal? One side becomes unequal. In orthorhombic, everything is unequal. Alright. So in hexagonal and trigonal, in hexagonal we have alpha A equals B is not equal to C, alpha equals beta equals 90 degree, and gamma is 120. This is a different variation. Gamma is 120 degree and the angles are 90 degree. Just remember this. Alright. Now triclinic. Triclinic is the easiest one. We don't have anything equal. Alright, so this is also easy to remember. Trigonal or rhombohedral. Rhombohedral is also easy to remember because we have all the sides equal and all the angles are equal, but the angles are not equal to 90 degree because rhombus doesn't have angle equal to 90 degree, because if angles are equal to 90 degree, it becomes a square. Just remember this. So this is easy. Trigonal, this also. The only thing is monoclinic. Alright, so monoclinic, you have to remember monoclinic. In monoclinic, we don't have any side equals. We have alpha equals gamma equals 90 degree and beta is not equal to 90 degree. Just remember this. Alright, and also regarding the variations, in cubic we don't have n-centered. In tetragonal we have n-centered. In orthorhombic we have all of the types that we have, all the 4. Hexagonal and trigonal, they are only primitive. Triclinic is also primitive. Monoclinic, we have primitive and body. Alright, so there's a pattern to this. Just practice this like 3-4 times. Just see the pattern, just appreciate the beauty, draw the structures. This would be like easy. It's not difficult. Nothing is once you practice it. Alright then. So this we have done. So now the question that rises is, why only 14? That's the bigger question that we have. Why only 14? So like we have 7 crystal system, that's what we have seen. So we have seen there are 4 variations that we can have. For each one, we can have primitive, body-centered, end-centered, face-centered. Now the question is, why not 7 crystals? So for each crystal we will have 4. For 7 crystal, how many we should have? 7 into 4 is 28. Why not have 28? That's the question. That's a good question. But the answer to that was discovered by Mr. Auguste Bravia in 1848. Yes, you heard it right. 1848. Alright, so let me introduce you to Mr. Auguste Bravia. 1811 to 1863. He, in 1848, mathematically proved that there can be only 14 variations possible of the crystal structures. What does that mean? It's a powerful statement. So in all the world, the crystals that we have, they can have only 14 variations. So the atoms can be at specific places. So either they can be body-centered, end-centered. Only 14 types you can have. All the arrangements that you can make, only 14. Why not more than 14? So before that, so in respect of Mr. Auguste Bravia, we named it Bravia lattices. So these 14 variations are what we call Bravia lattices. Remember, this is Bravia. That's the name. That's a French name. It's not Bravias. It is Bravia. Alright. Simple. Perfect. So why only 14? That's the bigger question. So the answer to that is symmetrical incompatibility. Incompatibilities. Now what does that mean? So let's say in cube, what did we say? In cube we said that we can have only 3. We have primitive, we have body, we have face-centered. Now the question is, why can't I have n-centered? Okay then, let's have n-centered and let's see. Okay, this is cubic unit cell. Now I have atoms at the corners. Now let's make it n-centered, because that is what we are demanding. Why not have an n-centered? Okay, let's have n-centered then. So n-centered we'll have at any two ends. So we have these two atoms now at n-centered. Now let's see the distance. So distance from this corner to this corner is not equal to distance from this atom to this atom. So this is what symmetrical incompatibility is. So this x is not equal to y. But if I go for the normal one, what we have for cubic, the body centered. So if I check body centered, what do we have in body centered? So I have at the corner and I have at the center as well. Now if I calculate the distance from the corners, each corner, so every distance would be the same. All x's would be equal. That is the one reason that we have symmetrical incompatibilities. That's why we don't have n-centered. So n-centered cube doesn't exist. That's the reason. The second reason is redundancy. Redundancies. Now what does redundancies means? Redundancies means we have repetition. Alright. So let's say if I talk about triclinic, in triclinic what do we have? Only primitive. Why can't I have body centered? The reason is, if I have body centered triclinic, so if I have one unit cell that is body centered triclinic, now if I keep one more unit cell that is body centered triclinic, this will form a geometry that is tetrahedral. Alright, so that's a repetition. The whole thing is, when you try to make something that is not there, like body centered triclinic, you make a structure that is already there. So that might be in tetrahedral or some other structure. So it is already there. So you try your best to make additional more than 14, but what you do is you end up amongst the same that were there before. So that's the other reason. So redundancies and symmetrical incompatibilities are the reasons that you don't have more than 14. And the other thing is, I want you to appreciate Mr. Auguste Bravia, that in 1848, when there was no technology, he gave the statement which we are still believing in after 300 years, more than 300 years. and the best part is, many scientists have, now we have modern technologies, we have tested Mr. Auguste Bravia, and he still is correct. That's mind-blowing thing. That's how long-sightedness, that's how more predictions can, scientific mind can take you long distances. Alright then. Now what I want you to do is, what I want you to see is to see the number of atoms that are present in a unit cell. So we said we have a unit cell, that is the smallest portion of the crystal lattice. Now what we want to see is, so if this is the smallest portion of the crystal lattice, how many atoms does this unit cell has? You know, how many atoms does this unit cell have? So I see there are 8 corners, but do they all of these atoms belong to this unit cell? The answer is no. Why? Because this unit cell has 8 corners, so there would be another unit cell, the same cubical one, then we will have up, down, so there would be more cubic unit cells which would be sharing this atom that is there. Alright, so I want you to remember one thing. So many people think, as we describe unit cell, so many people think like there is one unit cell, then I'll have one more unit cell. These are not individual unit cells. What happens is, I'll show you what happens. Let me take out my unit cell. Okay, so this is primitive unit cell, so I'll show you afterwards how this works. So what happens is, let's say these are the unit cells that we have. This is one cubic unit cell. So these two atoms are being shared by one more unit cell. Let me show you bolts. So these two atoms are being shared by these two other atoms that are there. So this is one more unit cell that is being formed by sharing these two atoms. It's not like there is a whole different unit cell that is being made. Alright then. So now let's discuss number of atoms in unit cell. Number of atoms in unit cell. So first, what I want you to see is primitive unit cell, primitive cubic unit cell. So remember this. So few assumptions for studying number of atoms in unit cell. We are considering the atoms, the constituent particles as atoms. We are not considering molecules or ions for the ease of understanding. So the constituent particles are atoms, and they are considered as hard spheres, which they are actually not. Alright, and the other thing is, we are considering cubic unit cell just for ease of understanding. So these are the 2-3 assumptions that we have made. Alright, so in case of primitive cubic unit cell, what do we have? We have atoms at the corner. At 8 corners. Does this look like cube? This doesn't. Let's redraw it. Okay, this is better. So the atoms are present only at the corners. Alright. So let me show you how it actually looks like. So this is the smallest unit cell. The whole crystal will be repeated. The whole unit cell will be repeated to form entire crystal. And the crystal lattice is what is inside the crystal. Alright. So now if I talk about this, so now let me show you a structure, where you have better understanding about what I am talking about. Alright, so look at this atom at the corner. So that is what we are talking about. Alright, so we are taking one cubic unit cell. So this is one cubic unit cell, the outer one. So let this, and we are talking about this atom. So this atom is being shared by how many unit cells? So 1, 2, 3, 4 in its layer, and the lower layer we have 1, 2, 3, 4. I'll show you how it looks like. So let's say if this is the cubic unit cell, so this is the atom we are talking about. So we have one here, alright, so we have one here, one here. So 4 in this layer, and same down layer, 1, 2, 3, 4. So this atom is being shared by, so this atom is being shared by 8 unit cells. Alright, so if I talk about this unit cell, so this is what I take out and I bring it here. So if I talk about this unit cell, so each atom contributes 1/8, because this atom is being shared by 8 unit cell. So the contribution of this atom to this unit cell is 1/8. Alright, so each atom, each corner, we have 1/8 contribution of the atom to this unit cell. So how many corners do we have? 8. And 1/8 is the contribution. One atom per unit cell is what we get. So this is how the primitive unit cell looks like. Primitive cubic unit cell. Right, so we are talking about any atom. So this contribution is 1/8. We have 8 corners. 8 into 1/8 gives me one atom per unit cell. Alright, now just remember this, because we will be using it describing other things. Now let's move on to body centered. Body centered cube, BCC is what it is known as. What do we have in BCC? As we discussed before. So this is the cube. So we have at the corners, and we have at the center as well. Body centered cube. That's why it is known as body centered, because there is an atom at the center as well. So now let's calculate the number of atoms that we have in this unit cell. So we have 1/8 into 8. Alright, so 8 corners, each contribution, atom's contribution is 1/8 to this unit cell. So total is 1. Then we have one more unit cell plus 1. The atom that is inside the unit cell, we have one more atom. So in total we have 2 atoms per unit cell. Alright, now the last one that we have in cube is face center. This is face centered cube. This is known as FCC. What do we have in FCC? We have a cube, atoms at the corner, and then we have atoms at the center of faces too. Alright, so before moving on, let me show you the BCC. Alright, so this is BCC, a beautiful structure. So atoms at the corner and atom at the center of the body. So that's why it is known as BCC. Just look at it, how beautiful the structure is. Atom at the corners and atom at the center of the body. Alright, so now if I talk about FCC, so this is unit cell. Alright, so now we have atoms at the corner. So if I look at the atom for the constituent at the space, at the face, atom at the face, what do I have? So if I extend this, there would be one more cube, just like this. So one more cube. So this atom is being shared by 2 cubes. Alright, so the contribution of atom to each cube is half. Alright, because this atom is being shared by 2 cubes, so it contributes half to this unit cell and half to the other unit cell. Alright, so now let me show you in the. Okay, so this is the face centered cube. Alright, so this is how the face-centered cube looks like. So each atom, the face center, so we have at the corners, you see white one, these are the corners one, and this, the face-centered, each face, you see each face. So these atoms are being shared, so there is one more unit cell out there which is sharing this face center. So each cubic unit cell has half. So the contribution is half. Alright? So this contributes half. How many faces do I have? 1, 2, 3, 4, 5, 6. 6 faces. So 6 faces into half contribution gives me 3 atoms. And obviously I have 1 by 8 into 8. So these are the corner ones. So this is 1. So in total we have 4 atoms per unit cell. Alright then, so this is how it goes. So we have 4 atoms for face-centered cube per unit cell. Contribution from corners, and we counted the contribution from the face center. Alright, so just before we end this part 1, so what I want to do is, I want you to see and appreciate this difference between FCC and BCC. Now some people might ask, why didn't I discuss the n-center for cube? The reason is cube doesn't have n-center. That's what we discussed. Alright? And we discussed the reason for that as well. Okay, so in FCC, what we saw, the atoms are present at the faces, centers of the faces. In addition to obviously the corners are by default. Alright? In BCC, what do we have? You have atoms at the center of the face, center of the body. Now due to this, the FCC are easier to mold. They are more ductile. That's the reason, because the atoms are present at the face centered. You see, the atoms present at the face centered. So when I put pressure, it is easier to mold as compared to the BCC one. Because in BCC, we have atoms present at the center of the body. So that's the reason. FCC are more ductile and easier to mold. So example for this would be copper, iron, nickel. So these are all FCC that we have. Face-centered cube. So this is what happens. So in copper, the structure of copper crystals, how the crystals are arranged, is in this manner, FCC, face-centered. All the atoms, so we will have copper atoms at the corners, then we will have copper atoms at the center as well, center of the faces as well. Alright, so this is what it is. This is no alien topic. Remember this. There's nothing alien that is going on. What we are studying is, we are studying structures around us. So the FCC is the structure of copper, iron, nickel. Remember this. Alright, so BCC is stronger as compared to FCC, because in BCC we have at the center of the body. Alright, so this is the thing that we have. Alright, so in this part what we have done is we have studied all about crystals, crystal systems, unit cell. In the next part that will come, what we'll study is about the packing, how the atoms are packed, how the different constituent particles are arranged to form the whole solid. How do we make solid? And also we'll study about defects. Right now what might seem is crystals are perfect. They don't have any whatsoever defects. But in the next part of this lecture, what we'll see is, you will see defects in the crystal system. You will see some atoms missing. Alright, so this is all that is for the next part. What I want to do is just go through everything that we have taught, and just remember this. This is all the nature around us, the surroundings that we are studying. This is no alien concept that we are studying. Alright, appreciate everything that we have studied and just try to relate it to your surroundings. I'm telling you, it's beautiful. Study solids. Alright then. So now, before ending, what I would like to do is, there are few thoughts that I write whenever I get free time. So I write these thoughts. It's all about education and science. Alright, so let me read the thought out to you. Education has become a heavy luggage that children want to remove as soon as possible. Education is beautiful. It has the power to transform lives. This world is beautiful. How can you not love learning about it? It is just that the education system has spoiled it for the young, beautiful mind. Thank you.